If the breathtaking images from the James Webb Space Telescope have amazed you, then what I'm about to reveal will absolutely stun you. The European Space Agency's Euclid Space Telescope has just released its first set of observations, and these might be some of the most extraordinary cosmic photographs ever captured. Called Euclid's First Light, this initial gallery is a brilliant panorama of galaxies, nebulae, and star clusters scattered across the universe. And scientists are genuinely stunned by what they're seeing. These images challenge long-held assumptions about how the universe evolved, shed new light on the intricate role of dark matter, and allow us to peer billions of years into the past, some photos showing galaxies more than 10 billion light-years away. And honestly, the pictures themselves are jaw-dropping, especially the final one. Today, I'll guide you through Euclid's early discoveries: shimmering galaxies, tangled nebulae, stellar nurseries, and even planets drifting freely through space. Together, we'll explore why Euclid is unlike any telescope before it, and how its observations may help scientists reconstruct the origins of the cosmos itself. Euclid launched on July 1st, 2023, lifting off from Cape Canaveral aboard a SpaceX Falcon 9. After a journey of roughly 1.5 million kilometers, it settled into orbit around the Sun-Earth Lagrange Point 2, home to the James Webb and Gaia observatories. This region is a perfect platform for deep space study. From L2, the Earth, Moon, and Sun always remain behind the telescope, allowing an uninterrupted view of the distant universe. It's also close enough to Earth for rapid communication and stable operations, moving in sync with our planet as it orbits the Sun. Euclid's 6-year mission focuses on uncovering how the universe is structured and how it has changed over billions of years. Its primary goal is ambitious: to construct the most detailed and expansive 3D map of the cosmos ever made. In October 2024, the telescope began returning the first fragments of this cosmic map, fragments I'll show you shortly. Over the coming years, these measurements may help scientists finally understand how gravity, dark matter, and dark energy have shaped the architecture of the universe. Before diving into the images, it's important to understand what makes Euclid truly special. First, Euclid's extraordinary field of view allows it to photograph enormous sections of the sky at once far wider than any previous space telescope, while still capturing incredibly sharp detail. It collects visible and infrared light from billions of galaxies, some located 10 billion light-years away. Compared to the best ground-based surveys, Euclid delivers 4 times the resolution and over 15 times the sensitivity in the near-infrared. It can identify objects hundreds of times fainter than what the Gaia telescope can detect. Each snapshot captures not only the large-scale cosmic environment, but also the fine structure inside individual galaxies. Second, Euclid detects minute distortions in galaxy shapes caused by gravitational lensing, the bending of light by dark matter. These distortions map the invisible framework of the universe, providing vital clues about how galaxy clusters grow, how cosmic filaments form, and how dark matter has sculpted the cosmos across time. Finally, Euclid's 2 scientific instruments work together to produce a 3D cosmic atlas. The Visible Imaging System, or WIS, captures ultra-sharp images to pinpoint the shapes and locations of galaxies. Meanwhile, the Near-Infrared Spectrometer and Photometer, or NISP, measures redshifts, placing each galaxy in 3-dimensional space. The result is a dynamic view of the universe in both position and depth. No wonder astronomers are thrilled. As Euclid project scientist René Laurages put it, "We have never seen astronomical images quite like these, so rich in detail and so exquisitely sharp. They reveal structures and features that were completely hidden until now." So let us begin our tour of Euclid's first light images, starting with its new cosmic map. Thanks to earlier ESA missions like Gaia and Planck, we already possess a detailed map of our Milky Way and the cosmic microwave background. Euclid's task is to fill in the vast dark spaces between the regions dominated by faint galaxies and the elusive influence of dark matter. So far, the telescope has charted only about 1% of its intended target. Between March 25th and April 8th, 2024, Euclid captured 260 exposures of the southern sky, an area 500 times larger than the full moon. Combined, these pictures form a sweeping mosaic containing millions of stars and galaxies. And again, this represents just a tiny fraction of the final map Euclid will assemble. Because Euclid records both broad cosmic structure and fine detail, Astronomers can zoom in from grand extragalactic landscapes to the hearts of galaxy clusters and even individual star systems within a single dataset. Let us explore some of these structures, beginning with one of the most immense galaxy clusters in the known universe. Here is the Perseus Cluster, located roughly 240 million light-years away. In Euclid's image, more than 1,000 galaxies belonging to the cluster are visible, along with over 100,000 more in the distant background. Scientists believe the arrangement of galaxies in this cluster reveals how dark matter threads through the universe. The leading theory is that dark matter forms vast filaments, cosmic scaffolding, that channel galaxies into clusters wherever these filaments intersect. Without dark matter, galaxies would be spread much more uniformly across space, which is clearly not what we observe. Cosmological models predict that clusters like Perseus should contain numerous dwarf galaxies, tiny, faint companions whose shapes and motions can help trace how dark matter is distributed. But these dwarfs are easily lost in the glow of brighter stars and infrared background light. Euclid, however, cut through the noise. It identified more than 630 previously unseen dwarf galaxies in the Perseus Cluster. Enormous advancement in understanding dark matter's influence on cosmic structure. But Euclid isn't only revealing dark matter. It's also transforming our understanding of star formation. Our next stop is the irregular galaxy NGC 6822, glowing softly 1.6 million light-years from Earth. First noted by Edwin Hubble in 1925. This galaxy has long fascinated astronomers. While JWST has imaged parts of NGC 6822 with incredible resolution, Euclid's wide-angle vision captures the entire galaxy at once, along with its surrounding environment. Scientists are especially interested in NGC 6822 because many of its stars are surprisingly low in heavy elements, what astronomers call low-metallicity. In the early universe, heavy elements were scarce because stars had not yet lived long enough to forge them. Studying galaxies with low metal content helps researchers reconstruct what galaxies were like shortly after the Big Bang. Euclid's instruments, especially NISP, provide detailed color information that helps astronomers identify regions of varying metallicity. The telescope has also uncovered new globular clusters and high regions, brilliant clouds of glowing gas ionized by newborn stars. These regions allow scientists to examine the physical conditions present when massive stars ignite for the first time. Speaking of globular clusters, Euclid also turned its gaze toward NGC 6397, a dense cluster only 7,800 light-years from Earth, one of the closest globular clusters known. Hubble imaged its core in 2021, but Euclid managed to photograph not only the core but the entire cluster and its sprawling outskirts, all in a single hour. Globular clusters are crowded stellar cities, where bright, massive stars dominate the view, but the faint, low-mass stars lurking in the cluster's outer regions are among the most scientifically valuable. They contain the chemical signatures and motions that preserve the Milky Way's earliest history. As researcher Davide Massadri explained, no other telescope currently operating can capture both the full extent of the cluster and its faintest stellar members with this level of clarity. Images like these may help answer deep questions about the evolution of spiral galaxies, including our own. Of course, the technology behind Euclid wasn't cheap. The European Space Agency invested roughly 1.4 billion euros into building, launching, and operating the telescope. For that price, scientists are eager to extract every possible insight about the universe. Next on our tour is Caldwell 5, sometimes called the Hidden Galaxy, located 11 million light-years away. It lies behind thick curtains of dust and crowded star fields within the Milky Way's disk. Despite being similar in structure to the Milky Way, it has always been notoriously difficult to observe. Euclid's infrared capabilities slice through the dust, revealing a crisp portrait of the galaxy that we've never had before. Its spiral arms, dust lanes, and star clusters all stand out with remarkable clarity, as Euclid Consortium scientist Leslie Hunt noted. What makes this image extraordinary is its versatility. The telescope captured the entire galaxy in a single frame. Yet scientists can zoom into individual stars and clusters. This allows researchers to trace star formation histories and examine how gas, dust, and dark matter interact to shape spiral galaxies. Now for the grand finale, Euclid's most visually stunning and scientifically exciting image. the Horsehead Nebula. Often photographed but never seen like this, Euclid captured the nebula with unmatched sharpness and an extraordinary field of view. And once again, this stunning image took only 1 hour to capture. Located around 1,375 light-years away, the Horsehead Nebula is the nearest massive star-forming region to Earth. It lies near Alnitak, the easternmost star of Orion's belt, within the vast Orion molecular cloud. This region is a treasure trove for researchers searching for free-floating planets not bound to any star. Euclid has already detected numerous new candidates, including very low-mass objects that had never been observed before. The bright background clouds are illuminated by ultraviolet radiation from the star Sigma Orionis, while the dark horsehead shape consists of cold molecular hydrogen, barely emitting any light. Comparing star formation in bright irradiated regions with that in dark, shielded clouds may reveal how different environments influence the birth of stars and planets. Sigma Orionis itself belongs to an open star cluster rich in stellar and planetary objects, including free-floating planets. With Euclid's sensitivity, scientists discovered many more of these rogue planets than expected, suggesting they may be far more common than previously believed. And this is only the beginning. With more than 5 years of observations still ahead, Euclid will continue to map the cosmos, uncovering new structures, refining our understanding of dark matter and dark energy, and revealing how galaxies and stars came to be. A full 3D map of dark matter could fundamentally reshape our understanding of physics. Until then, we have these remarkable images and many more still to come. If you are interested in astronomy, astrophysics, cosmic science, or the mysteries of space, subscribe to the channel for new videos every day. Thank you for watching.